Hi everyone. We'll start out today's video with another comic from XKCD. So skip forward a few seconds if you don't want to watch it or listen, but pause it if you do want to take a look at it. It's how worried you should be when various things happen to you in real life versus in the movies. And if you understand it, I think it is mildly entertaining. In this video, we're going to cover section 5.3, diagonalization. Still relates to the main topic of this chapter, which is eigenvalues. And we start out talking about powers of a diagonal matrix in this first example. So let's see, powers of a diagonal matrix. Diagonal matrix. There we go. So if I have this diagonal matrix D here, 5, 0, 0, 3, if I square it, D squared, that is D times D, 5, 0, 0, 3, times 5, 0, 0, 3, multiply row by column, 5 times 5 is 25 plus 0, row by column, 5 times 0, 0 times 3, that stays 0. Then this row by this column, 0 times 5, 3 times 0. And then the last row by column, 0 times 0, 3 times 3 gives me 9. Notice how only those diagonal entries changed, nothing else. So if I want D cubed, the same thing happens again. You would have 125 here, 0, 0, and 27 there. So that's kind of interesting. D to the kth power, easy, right? You just multiply those entries to that power. So you have 5 to the k, 0, 0, and then 3 to the kth power. There's not much computation involved in that. We have a formula for that. So what is kind of cool, if I have a diagonal matrix D, or if I have A is similar to a diagonal matrix D, A equals P, D, P inverse. So if A and D are similar, and I want to compute A to the kth power, that is P, D, P inverse. Actually, let me just start out with A to the second power, A squared, P, D, P inverse squared. Well, how do I do that? Well, I multiply P, D, P inverse by itself, P, D, P inverse, and watch what happens when I drop the parentheses. P, D, P inverse, P, D, P inverse, right here in the middle, P times P inverse, that is the identity. So what we're left with is P, D times D is D squared times P inverse. So if I have A and D are similar to each other, I can find A to whatever power I want to using PDP inverse, using that relationship. So A to the kth power is P times D to the kth power times P inverse. And what you really like, the value of that is computational time. If A is 500 by 500, and I want to multiply by some power, think about how many individual calculations are involved with a 500 by 500 matrix to the 15th power. That's a huge amount of computation. But if I have that it's a similar to some diagonal matrix, the computational time is reduced incredibly small. So that's kind of the value of this relationship here. A little vocabulary here on the bottom. If A is diagonalizable, it is similar to a diagonal matrix. So that's what the word diagonalizable means. New word you might not have heard of diagonal before, but we could throw all that suffix stuff at the end there, diagonalizable. That just means it's similar to a diagonal matrix. All right, so in this example now, we have a matrix A, and we are going to come up with a formula for A to the kth power, and we're given D that it's diagonal to, or that it's similar to, and then the matrix P. But what we also need to find is P inverse, and luckily we have a formula for that, 1 over the determinant times switch 2, negate 2, so I'll switch these two, -2, +1, and negate that one, and that one becomes a +1. And what is my determinant for P? 1 times 2 times -2 is -2 minus 1 times -1. So that would be plus 1. -2 add 1 is -1. And so my entries are now 2, 1, -1 for P inverse. Okay, so if I want a to the kth power, let me just erase that there. There we go. If I want a to the kth power, that is P d P inverse to the kth power, which we just saw on the previous slide, that is P times d to the kth power times P inverse. Now I'm going to plug in my matrices. P is 1, 1, -1, -2. D is 5, 0, 0, 3. That guy to the kth power times 2, 1, -1, -1. And then that matrix to the kth power is 5 to the k, 3 to the k. So I'm just going to erase my little k there. There we go. And now when you simplify that, when you do the multiplication first, multiply the first two matrices, then that product times the third matrix, you end up with, it's kind of ugly looking, but it computes a to any power that I want to with a pretty simple calculation. 2 times 5 to the k minus 3 to the k. Below that, 2 times 3 to the k minus 2 times 5 to the k. And then 5 to the k here minus 3 to the k. 2 times 3 to the k minus 5 to the k. Okay, again, kind of ugly looking, but it is a formula. And that's as simplified as this one gets. If you multiply any of the 2 times 3 or the 2 times 5, that would mess things up. Because the 3 to the k has a power, so it's incorrect to multiply the 2 times the 3. All right, and if you want to see where they came from, well, just go row by column and do that out at first with the first two matrices and then times the third one. Next up, we're introduced to a proof called the diagonalization theorem. So we have an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So that's how we know if our matrix A is diagonalizable. So if it is similar to some diagonal matrix, if it has n linearly independent eigenvectors. And then the second part is even more important, more significant. In fact, if A equals PDP inverse with diagonal matrix D, if and only if the columns of P are the n linearly independent eigenvectors of A. In this case, the diagonal entries of D are the eigenvalues of A. So a matrice's eigenvalues are in its similar diagonal matrix. Those two things are very closely tied together. Our text has a proof of this theorem. I'm going to leave that out and focus more on the computation in this case. All right, now we come to an example where we're going to use that theorem to, quote, diagonalize our matrix, diagonalize that matrix. So I'm going to break this up into, I think, 4 general steps. Step 1, first we're going to find the eigenvalues of our matrix A. That's going to be step 1. To do that, this is from section 5.1. We're going to set 0 equal to the determinant of A minus lambda times the identity. And I'm going to not write out every step. This is 5.2, excuse me. 5.2. I'm going to not write out every step of this process and leave that to you to go back and refresh yourself of the last 2 sections if you need to. So I'm going to skip right to what that determinant is. Okay, and that determinant of A minus lambda I simplifies to negative lambda cubed minus 3 lambda squared plus 4, and that's equal to 0. When you solve that, and you can use the factor command in your calculator, and it will factor it into negative lambda minus 1 times lambda plus 2 squared. So that tells me my eigenvalues are lambda equals 1. That has a multiplicity of 1. Lambda equals negative 2. That has a multiplicity of 2. Okay, so that's our first big step, and if you need to refresh your memory on that, that's 5.2. Go back and watch the video. You know, you'd love to listen to me drone on for 20 minutes again, talking about eigenvalues. Now our next step, step 2, we're going to find 3 linearly independent eigenvectors of A. Eigenvectors of A. Okay, so once I have my eigenvalues, now I'm going to go find my eigenvectors. And this is from section, let me just circle that there. This is from section 5.1 where we did this. All right, so from 5.1, if lambda equals 1, that corresponds to an eigenvector v1 equal to 1 minus 1, 1. Okay, and I just skipped like 14 steps right there. But if you go back and look at 5.1, once we're working with lambda equals 1, we solve a minus 1 times the identity, x equals 0. And in representing that solution, the non-trivial solution, that's the vector that it produces. All right, so that is for lambda equals 1. Okay, then lambda equals -2. All right, what are we going to do there? That produces two linearly independent eigenvectors. V1 is equal to -1, 1, 0. And V2 is equal to, let's see, -1, 0, 1. And since there's two of them, we can pretty quickly check that they are linearly independent. And if you take a minute, they are, definitely. They don't scale each other. Okay, so that is step 2, 3 eigenvectors of A. Then step 3, we can write down our P, and then a step 4, we can write down our D matrix. Okay, so P is formed from the eigenvectors from V1, V2, and V3. And oops, I should have called this V2 and this guy V3. There we go, that's better. So P is formed from those three vectors. So P is equal to, let's see, 1 minus 1, 1, minus 1, 1, 0, and minus 1, 0, 1. Boom. That's the P matrix. And then step 4, our diagonal matrix. D is formed from the eigenvalues. From the eigenvalues of A. So D is equal to 1, 0, 0, 0, -2, 0, 0, 0, -2. And there's my diagonal matrix D. And then one additional step we could take, or we might be asked to do, is to check and verify that if, well, A equals PD, this one's a P, P inverse. If I multiply by P on both sides, since I don't have P inverse right now, although I could find it pretty quickly, we can check AP equals PD, because that's the identity, to make sure that we did our work correctly. Okay, you could type P inverse into P into your calculator and then invert it that way if you wanted to. There's a lot of different ways to the steps that we could take next, but we've basically done what they asked us to do: diagonalize the matrix, if possible. It is possible. And by the way, before I conclude this problem, technically, once I got those two numbers, at that point back there, I could have written down my diagonal matrix D, right? But I didn't write it down until the end. Cool. In this next example, we encounter one where something a little bit different happens. So again, it says diagonalize the following matrix if possible. So we'll go through our steps here. Step 1, 0 equals the determinant of A minus lambda times the identity. And you get, in factored form, actually the exact same characteristic equation, which is kind of cool. It is a different matrix. Feel free to go back and check a minute ago in the video. Different matrix produces the same characteristic equation. So they have the same eigenvalues. For lambda equals 1, that corresponds to an eigenvector. So this is step 2. V1 is equal to 1 minus 1, 1. And then lambda equals -2. That corresponds to an eigenvector V2 of -1, 1, 0. And that's it, just that vector. So even though lambda equals -2 has a multiplicity of 2, it only produces one eigenvector when we solve a minus lambda I x equals 0. So because of that, we cannot construct a basis for R3 using the eigenvectors of A. Eigenvectors of A. By Theorem 5, A is not diagonalizable. Diagonalizable. Love writing that word. All right. So if I had gotten 3 different eigenvectors, the eigenvalues that each produced one eigenvector, great. But because we had that one with a multiplicity of 2, the lambda equals -2, we're not guaranteed to get 2 eigenvectors out of that. We can get up to 2, but not. We don't have to get 2 different vectors, 2 linearly independent vectors out of that. Okay, so that one's not diagonalizable. What's cool, though, is even though it has the same exact characteristic equation, so that was kind of cool. Theorem 6 is a pretty quick one. I'm not going to do any proof of it. It's in the book, but it's one that hopefully makes sense. I kind of just said it a moment ago. If I have an n by n matrix that has n eigenvalues and they have the word distinct there, that means that they're all different. Distinct. So if there's like 1, 2, 3, 4, 5, if it's 5 by 5, and distinct and different eigenvalues, it is therefore diagonalizable because each of those eigenvalues will produce one eigenvector, and therefore we can have a basis for our n. There we go. Next example, 5. Determine if the following matrix is diagonalizable. This one's quick, but it involves understanding the theory. First thing to notice is we are triangular, right? There's zeros below the main diagonal, so we're upper triangular. Then you have to know, well, if it's triangular, the eigenvalues are on the main diagonal. 1, 2, 3. So let's write some of this down. A is upper triangular. So the eigenvalues are on the main diagonal. Okay, then count them. There are 1, 2, 3. There are 3 of them. So A is 3 by 3 with 3 eigenvalues. So by Theorem 6, A is diagonalizable. Cool. That was, like I said, not a lot of work, but you got to understand the theory and be familiar with it in order to like get all of that. All right, now we get to our last theorem of the section. Theorem 7 involves matrices whose eigenvalues are not distinct, so not like the last example that we just did. Let A be an n by n matrix whose distinct eigenvalues, lambda 1 through lambda p, for part A says for k between 1 and p, the dimension of the eigenspace for lambda k is less than or equal to the multiplicity of that eigenvalue. That's what we saw in the earlier example, right? You have a multiplicity of 2. You can have an eigenspace consisting of 1 or 2 vectors, 1 or 2. The matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. So if I only have fewer than n eigenvalues, the sum of the dimensions of the eigenspaces has to equal n. So if I'm in 4 dimensions, I need to have 4 linearly independent eigenvectors, which should hopefully make sense because we've seen that now. And this happens if and only if the characteristic polynomial factors completely into linear factors, and the dimension of each eigenspace for each lambda k equals the multiplicity of k. And I'll leave D for you to read on your own. This theorem, it's a little wordy. You might have to read it a few times to really delve into to really understand what it's saying, but I'll leave that one to you. Our last example, we'll go through one more where we diagonalize our matrix, and you can tell again, since we're triangular, in this case lower triangular, the diagonals. I can already tell what they are on the main diagonal there, and they both have multiplicity of 2. So I don't, because there's only 2 of them, so I don't know yet if it is diagonalizable. But what we'll do here is we'll say lambda equals 5 and lambda equals -3. Both with a multiplicity of 2. Okay, so lambda equals 5 can produce 1 or 2 eigenvectors. V1 in this example is -8, 4, 1, 0. And is there a V2? Yes, there is. V2 is -16, 4, 0, 1. And again, I'm skipping like 14 steps there. Not really 14, but a bunch of steps there. The steps that are in between, let me use a different color. The steps that are in between this and this are solving a minus 5i times x equals 0 and representing that solution. Those are the missing steps. All right? And then lambda equals -3. How many eigenvectors does that produce? The suspense is unbearable, I'm sure. V3 is equal to 0, 0, 1, 0. And V4, of course, is 0, 0, 0, 1. So now at this moment, I know that it's diagonalizable. Even though I could have written down a diagonal matrix D with 5, 5, 3, -3, -3 on the diagonal, I wouldn't have known that it was the correct diagonal matrix for this matrix until I've done this work. Okay? So the set V1, V2, V3, V4, that was a 4, is linearly independent by Theorem 7. So linearly independent by Theorem 7. So our matrix P is those 4 vectors, V1, V2, V3, and V4. And it is invertible. And A equals PDP inverse. PDP inverse with P equal to those eigenvectors. Let's see, the first entry is -8, 4, 1, 0, -16, 4, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1. And then D is equal to, that's our diagonal matrix, 5 with 3 zeros, 0, 5, 0, 0, 0, 0, -3, 0, that's a 0, and 0, 0, 0, -3. Boom. Okay, so there's one more example of working this out. If you have questions on diagonal matrices, how to find eigenvalues, eigenvectors, please send them my way. I am more than happy to work on these with you, or maybe I'll throw a video up for everyone just kind of going through this process in more detail. Maybe you don't like that I skipped 14 steps up here. I'm fully capable of making another video and drone on for 5 or 10 minutes and go through those steps if that will help you. I would be happy to do that. So please let me know if you have any questions. Thanks for listening.